This is a production of Cornell University.
Thanks, Alan. See if that stays up there. So it's fun. I've been the director of the National Museum now for 23 months, and it's a pretty phenomenal place. You've probably all been there at one form or another as a visitor. We get 7 million visitors a year, which makes it the most visited natural history museum in the world. And there's 127 million objects in the collections and 400 scientists. Last year did research in 70 countries and published 392 new species. So it's a pretty cool place, complicated place to get your hands around. What's cool for me about it, and the reason I came from Denver to the museum, was that of those 7 million visitors, 85% of them are unique visitors. They're tourists, which means that every year there's a different 85% of 7 million, which means over a decade we'll see something like 60 million people in the building, which is amazing, which means that equivalent of 20% of our nation will walk into that building in a decade. So it makes it one of the most visited informal science places in the world, if not the most. And that was what attracted me there, was this perception that it's really important that we communicate with people about science in a very effective way. And we know that kids are scientists because they're curious. And somehow they lose that curiosity. Some of them do, some of them don't. But whatever it is that persuades people to keep being curious, part of that is this perception that science is a valuable part of our culture. So it's an interesting place to be working because the potential is huge. The potential to put those 127 million objects and those 400 scientists and those 7 million visitors together and stir them up is pretty cool as a potential. And it's fun to come here to Cornell. I came because I was invited by Alejandra Gandolfo, a longtime collaborator. She and I have worked in Patagonia for a long time in amazing projects and related to what I'm talking about today, but I'm not going to talk about the Patagonian stuff, so make sure you get Alejandro up here to give a talk about the cool Patagonian projects soon. I also came to visit David Skorton, who is your president and soon to be our secretary of the Smithsonian. And the handoff is going to occur sometime next spring. He's going to come to the Smithsonian on July 15th. So it's great to get back in Cornell, and thanks for inviting me. I want to talk about origins of biomes. And if you look at this map of the tree canopy of the world today, you see that the world is by and large not that forested. But the forests that do exist occur in some pretty distinct patterns. You can see the tropical rainforests. You can see the bands of boreal forest. You can see the coastal rainforests, and you can see the deciduous forests, and then a whole lot of white space. But as a paleontologist who thinks about deep time, the evolution of plants, but also the evolution of the landscapes that host different kinds of plants, in particular trees, I kind of wonder how that pattern came to be. And with geologic time, you have both the evolution of different plant lineages. You also have the continents themselves are in play. The continents are moving at some fairly good speeds, actually. Continents kind of trip along at certain points in Earth history. Continents can move several inches a year. And over the millions of years of time over which plant evolution is happening, the continents are moving around and banging into each other. And we have this phenomenal fossil record on the planet. And I think we're so lucky that our planet buries its dead, right? It didn't have to be that way. You could imagine a scenario where a planet didn't bury its dead, but because of the rock cycle, as mountains erode and the debris from mountains gets deposited in low-lying areas, the corpses of plants and animals get buried and entombed, and those layers of rock hold the record of the planet. And so we can sort of ask the question, how did that modern configuration of forests actually come to be? What was the pathway to get there? And we've got additional information that's kind of interesting and useful. This is Dana Royer's curve that shows the last 600 million years of our best guess at carbon dioxide in the atmosphere and our best guess of when ice was prevalent. And one of the biggest surprises for most people is that our present planet, a planet that's frigid on the ends and warm in the middle, in fact, was not always frigid at the ends. It's always been warm in the middle, but not frigid on the end. So, in fact, the periods of ice, and there are two great big ice house periods, one around 300 million years ago, and one for the last 34 million years. But for the vast majority of the last 600 million years, the planet has not had polar ice caps. So our present world is kind of this weird anomaly relative to the history of the planet. And that makes you wonder about how forests fared in these different worlds, in these greenhouse worlds. So greenhouse world, icehouse world, two great big mega patterns. The last 70 million years shows warming at about, a warm planet at the end of the Cretaceous into the Paleocene, with a spike in the early Eocene at 55 million years, a really warm period at 50, and then a gradual decline. About 34 million years ago, the passage between Antarctica and South America opens up and the world cools dramatically. It warms back up in the Miocene and it cools to the present time period. And we don't really get ice in the northern polar areas until about 5 million years ago. So in fact, those earlier ice periods, when there was no land in the Arctic, were actually unipolar in their ice coverage. So we're living in a bipolar icy world for the first time in Earth history for the last 5 or 6 million years. So the present distribution of forests must arc through that story somehow. The fact that ice comes and goes, the continents move around. And hopefully that'll pop back up there. I ran into this dramatically when I was an undergraduate and got lucky enough to spend 2 summers in Ellesmere Island, about 1,500 miles north of the Arctic Circle, as part of an expedition to the Arctic in search of Eocene fossils. A woman named Mary Dawson at the Carnegie Museum in Pittsburgh had posited that the fossils that were found in the Paris Basin in London and the Bighorn Basin in Wyoming were similar enough. There must have been an Arctic connection during the Eocene. She said, there was some way that these would cross over the Arctic. And she went to the Arctic with the idea of finding the earliest pre-Ice Age fossils in the Arctic. And she went to Ellesmere Island, which is an amazing place. It's the size of England, and it's got about 200 people in it, mainly Inuits. Hopefully this will keep going on. That's Ellesmere in the middle there. And her first trip in '79, she found fossils, and what she found was amazing. She found fossil crocodile teeth, 1,500 miles north of the Arctic Circle, which was surprising to her and everybody else. I went with her the next couple of years, and flying around in this area that's so far north that there are no trees at all. In fact, the one species of woody plant is the Arctic willow, which is prostrate. So there's not even bushes in at this latitude. And this is an area where the permafrost goes down for over 1 kilometer in depth. The mean annual temperature is minus 30 degrees. There's 3 months of sunlight in the summer and 3 months of darkness in the winter. And the further north you go, the more that barrier is. But if you fly around, you see tremendously thick coal seams. And the coal seams themselves are full of those white rocks, when on close inspection, are actually tree stumps. So here we are 2,000 miles north of the nearest tree, and there are stone tree stumps. And when you date these rocks, they date around 55 to 60 million years old. So the peak of that warming, instead of ice caps, you have forests, which is a pretty amazing observation. I mean, I think if you had to say 2 words to anybody to talk about the impact of climate change, just say the words polar forests or Alaskan palms. And here's these forests, they're lying there. And the coal seams are amazing. We found coal seams that are up to 150 feet thick. So some of the thickest coal seams in the world are actually polar forest coal seams. And if you rummage around in the footage of these coal seams, you find ample vegetation. The conifers are not the Pinaceae that you find populating the boreal forests of today. They're in fact relatives of Metasequoia, Sequoia, Glyptostrobus, Taxodium, the cypress, the warm conifers that are present mainly in places like the Gulf of Mexico and the Yellow River in China. They're mid-latitude warm conifers. And these are the dominant conifers. And you find a variety of other things like these fragments, and paleontologists and paleobotanists are experts in fragments. We primarily deal in fragments. So you might not immediately see that as besides the fact that it's totally out of focus, you might not recognize that as the center part of a lumbo. So we can tweak this. I mean, it's sort of missing about half, right? It comes and goes. Okay, just thinking. And here, I noticed as I walked around the campus today, there's tons of beautiful Cercidophyllum trees on the campus here. And Cercidophyllum is one of the more common things that we see in these polar forests. So you have this interesting world that kind of looks like central China. except it's 2,000 miles north of the Arctic Circle. So those early trips in 84 and 85 drilled into my brain that the planet is really different today from what it was 50 million years ago. I mean, dramatically different. And here's a diorama that I built for the American Museum in New York of the high Arctic 55 million years ago. And you have a dense forest, you have these big crocodile animals, there are flying lemurs, there's crocodiles and turtles and snakes, there's lotuses. That's your Arctic in a warm world. And one of the things we've learned about the gradient is today, if you think about the temperature gradient from the equator to the pole, minus 30 degrees at the pole, plus 30 degrees at the equator today. So there's, from the equator to the pole today, there's a 60 degree centigrade gradient, a mean annual temperature. In the Eocene, the equator was somewhat warmer. We don't know exactly how much, but let's say 35 degrees C. And it looked like the polar regions had a mean annual temperature around 10 or 15 degrees. So the gradient is much, much smaller. Another way to think about that is that when climate changes, it changes much faster in the Arctic regions. In a warming climate, it'll warm 5 to 6 times faster than it does at mid-latitudes. Which is interesting because it means if you want to see the future now, go to the Arctic because it's happening faster there now. So here's the Arctic today. I mean, if you go up there, it's quite a phenomenal place because it's an ice scape, and it's both the permafrost on land and the floating sea ice at sea. And in 2005, there was an amazing paper published by an American-European coalition that had gone out to the middle of the Arctic Ocean, and there's a submerged ridge in the Arctic Ocean called the Lomonosov Ridge. And you can see this ridge going across. It's now about 8,000 feet down in the bottom of the ocean. And they drilled the Lomonosov Ridge and brought up seafloor samples, expecting to see the marine foram, the marine plankton record of the ancient Arctic Ocean. And what they found was really startling. They found the spores of the floating aquatic fern Azolla. So here you have an Arctic Ocean that in fact not only wasn't producing marine forams, it was producing freshwater fern spores in great abundance. And here's, you've all seen Azolla, that's what it looks like. And there were layers in these rocks that are 47 to 50 million years old of Azolla spores. So you have this crazy situation of an Arctic Ocean that must have had a freshwater lens on it, which makes some sense. You have a closed basin and freshwater runoff into the Arctic Ocean. So a freshwater lens lake floating on top of a deep saltwater basin. And on top of that lake were floating aquatic ferns. So here's a lake in Amazonia. I love going to Amazon. It's a great busman's holiday if you ever want to go and experience delightful times. But out in central Amazonia, there are these gigantic lakes that are so big you can get on a small boat and not see the edge of the lakes. And the lakes are often totally covered in Azolla. So here's an Amazonian lake that is actually the Arctic Ocean of 50 million years ago, which is, you know, actually kind of a very compelling thought to realize the planet has changed that much. And most people, you know, have no idea of the Arctic wasn't always polar. And in fact, polar Arctics, well, that is technically polar, let's just say frigid. Frigid Arctics turn out to be the exception, not the rule. And it's pretty unclear exactly how the physics of that works, because we all know that there's more sun at the equator and less at the poles, and the Earth's tilt is still there. So how you keep the Arctic warm in a dark winter is an unresolved mystery that there's some modeling progress on, but we don't understand that exactly. And it's not like this is just a chunk of land that floated up there, because we have the same kinds of fossils all around northern Russia, and in fact, Antarctica as well. So there's a very good, well-documented saga of warm polar regions in the warm world of the Eocene and Paleocene. Which sort of begged the question to me, when did tropical rainforests start? And the second part, a little bit less intuitive, is where did they start? Because they happen to be in the equatorial regions now, we assume that they must have started in the equatorial regions. But I think that might be flawed logic. Now there's some argument for that. And just to sort of introduce you to my basic tool, which is the humble leaf. As a paleobotanist, we find leaves pretty frequently. You could be a paleobotanist with your charcoalified flowers like Bill Crepé and Alejandra do here, Or you can look at pollen grains, and those are all great ways to look at fossil plants. And fossil plants are great because they represent plants in many different forms: tree trunks, pollen grains, charcoalified flowers, or leaves. But I'm a leaf guy. I like leaves. And leaves are pretty compelling things. And there's lots of them. A single tree can have like between 100,000 and 1 million leaves. I mean, I actually cut a tree down once and counted the leaves just to prove that. 99,284 was the number of leaves on my tree, or 50-foot tall red maple. And if you look at a leaf like this, a classic tropical rainforest leaf, it's got a couple of very distinctive characteristics. One, a very smooth margin, and this elongate, narrow tip, also called a drip tip. And this was noticed by a guy named Bailey, who used to work here back in the day, and published in 1915 this observation that leaves are actually indicators of climate, that smooth margin leaves are more common in warm climates, and that drip tips are indicative of very wet places. In tropical rainforests, many of the leaves have these features. We did a survey in Yasuní in Ecuador and looked at 400 species, and something like 70% of the leaves had smooth margins and elongated drip tips. It's a convergent forcing thing that show up in tropical rainforest in very wet areas. Not all tropical rainforest leaves have drip tips. Not all have smooth margins, but the percentage with smooth margins and drip tips is much higher in wet tropical rainforests. And here would be, this is actually my bedspread in my hotel in Manaus. And I've just laid out a sample of leaves from an Amazonian stroll in the woods. And what you see is that by and large, the leaves are large, they have smooth margins, a lot of them have drip tips. That's a classic tropical rainforest, modern tropical rainforest looking kind of leaf assemblage. Now this is a curve that shows you without years, but these are the stages of the Cretaceous period. So Bohemian's like 130 million years old, and Cenomanian's about 95 million. So it's from 130 to 95, and then from left to right is paleolatitude, with the equator in the middle, north latitude to the right, south to the left. And this shows the first occurrence of angiosperm pollen grains. A very old slide. There's probably better slides showing this now. But what you see is that some of the earliest angiosperms appear at low latitudes, equatorial latitudes. It's not a great data set. You can see there's a strong bias towards mid-latitude northern hemisphere stuff, which just reflects the location of paleobotanists more than anything else. But you see that by the Cenomanian, at both poles, north and south, angiosperms are present at the poles. So angiosperms appear, Darwin's abominable mystery, they appear apparently right at the end of the Jurassic, beginning of the Cretaceous, apparently somewhere equatorially, and very rapidly cover the globe. So by 100 million years, you've got angiosperms from pole to pole. In a world with no ice, you can do that. Right? So you would think, oh, there it is. The first angiosperms are equatorial. Tropical rainforests are equatorial. You can read many textbooks of those say, well, tropical rainforests have been around for hundreds of millions of years. They form in the equators. That's why there's diversity, because they started there, they've been there a long time. But if you actually look at the fossils, these early Cretaceous fossils of angiosperms, they don't look like tropical rainforest leaves. They're actually quite lobed and small. They don't have drip tips. In fact, Cretaceous leaves throughout the Cretaceous have a tendency to be a variety of different shapes that might even fit more with your mental image of what a deciduous forest would look like. And that's not an oak, but it looks like an oak. It's probably more closely related to a laurel. But there's a lot of these repeated shapes. These lobed leaves are pretty common in Cretaceous floras throughout the Cretaceous. And this, in fact, this assemblage is from the last 2 million years of the Cretaceous. So you've got this world where you find them, the leaves don't really look like tropical rainforest leaves. And I spent a lot of time chasing this problem around, and I finally found an equatorial flora in Bahariya Oasis in Egypt in 2000. And the leaves I found were small, lobed leaves, right on the equator 100 million years ago. So it's an interesting question, like where, if those are tropical rainforests, when did they start and where do they start? It starts to be a little bit more compelling to me. And if you look at a reconstruction of the world 80 million years ago, which is in the late Cretaceous, you're confronted by one kind of dramatic fact, which is there wasn't that much land at the equator 80 million years ago. So even if you wanted to put tropical rainforests at the equator, there's not really much place to put them. You've got to have land to put a forest on it at the end of the day. You can see that the great open ocean, the Tethys Sea, separates North America and South America, separates Africa and Europe, and separates India and Asia, and separates Australia into Malaya. So there's a great big east-west seaway in the Cretaceous that during the time of angiosperm evolution and diversification was clearly a barrier for the presence of large tropical rainforests. The big exception being the northern tip of South America, the northern part of Africa, and the southern tip of Indomalaya. So those would be places you want to go look if you want to answer that question. So again, Morley in 2000 published a book about, a very speculative book based on pollenology primarily, about his guess of the origin of tropical rainforests. And he basically proposed that during the warm Cretaceous, if you warm the planet up, the equator gets drier. And then he sort of predicted two sort of mesic wetter zones to the north and the south, but a dry equatorial region. Ziegler and his students in Chicago, looking at the distribution of different rock types, have shown that the horse latitudes have been persistently dry through Earth history. So you've got those deserts north and south of the equator, and the question is, was there in fact any persistent wet areas at the equatorial regions at all? Now, the other way I backed into this question was by studying the fossils of the American West, and in particular what happened to plants at the Cretaceous tertiary boundary, the event where the asteroid strikes, smushes the dinosaurs. And my question was, what did it do to the ecosystems? And that involved collecting about 100 different quarry sites, about 12,000 fossil leaves in the rocks that had dinosaurs, looking at the pollen, the leaves, the dinosaurs. And what we saw there was a diverse lobed-leafed Cretaceous flora gives way to a varied non-diverse early Paleocene flora of basically wetland plants. And that was the picture we saw in North Dakota. We took that work down to the Denver Basin. When I moved to Denver in 1990 and started excavating around Denver, and Denver turns out to be an amazing place because it's in the Denver Basin. It's a sedimentary basin that most of the rocks beneath downtown Denver are late Cretaceous or Paleocene in age. So I moved to town. The first week I was there, they were building the Denver International Airport. And I got a call from a workman out at the airport who said, we found a gigantic fossil fish. I was like, that's awesome. So I raced out to the airport. And what they had found was a palm frond. Which, if you've never seen a palm or a fish, might look like the tail of a fish. And we found huge palm fronds all over the site of the airport. When you fly into DIA, you're flying into a Paleocene palm forest. And one of the most traumatic experiences of my early curatorial life was watching a big track hole bury an 11-foot long pinnate palm frond on a big slab of rock that's underneath like runway 2 right now. But I realized that, God, I moved to a museum that's literally built on the KT boundary. In fact, the KT boundary is in between the museum and the airport. And downtown Denver is in Cretaceous rocks. And in 1992, we found a Tyrannosaurus rex in a backyard. It was the 11th known Tyrannosaurus rex at the time. We found several other dinosaurs in neighborhoods in Denver. And we started going out to construction sites. And one of the great things about plants is they're more common than animals. And so you might find one dinosaur, but for every dinosaur you'll find thousands and thousands of leaves. And we started collecting fossil leaves. And we collected about 200 sites in the Denver area. And what was cool about Denver was that the Rocky Mountains were coming up exactly at the end of the Cretaceous period. So the Denver Basin not only recorded the Cretaceous tertiary boundary, it also recorded the uplift of the Rocky Mountains and the creation of topography. So we had landscapes that ranged from near montane out into flat, swampy landscapes. So we also had adaptive conditions on a landscape as well as change through time. And in 1994, I was sitting in my office, and this guy walked into my office, and he had a cardboard box. And he had been by the side of the road, 25 miles south of town, on Interstate 25 in a place called Castle Rock, Colorado. And he walked in carrying 4 leaves. And the leaves were great big smooth margin things with drip tips on them. And I had just gotten back from the Amazon. I'm like, where'd you get these things? He said 25 miles south of here on the side of the interstate highway. So we went down there and dug into this outcrop. And it's the most nondescript outcrop you can imagine. I mean, there it is, it's like a slumped hill. Those blue tarps are the holes we dug. And here's the guy with one of these leaves. I always use some people for scale. It's quite handy. But here's a 24-inch long leaf, a big leaf. I mean, it's like this long. And we dug into this site immediately, and fossils were pouring out of the hill. I mean, it was unbelievable, everything you'd found. And what we actually found was that there was a buried soil horizon, and for about 8 inches above the soil horizon, there were just layers of leaves. So it was basically a forest floor that was flooded. And these leaves are lying in there in tremendous abundance. And of course, we're on the side of I-25 with 5,000 cars an hour going past us. And we had a lot of media showing up, and we were pulling these great big slabs out of the ground that were curious because people have known about fossil leaves in the Denver Basin for a long time, but they had never found a site like this before. This site was unique. It had really big leaves. It had a great diversity of species. A lot of the leaves had smooth margins and drip tips on them. I'm like, you know, it looks like a rainforest, smells like a rainforest. It just happens to be latitude 39. At the time, we didn't know the age of it, and I was thinking, well, it must be from the early Eocene, because that's the really warm time. What was also great was the fossils were extraordinarily well preserved. A lot of them had cuticle, and the leaves would just simply peel off the rock. And it was kind of tragic. You'd split the leaf open, and the leaf would just peel off and blow into traffic and get run over. And what was amazing about it, too, was that now, having spent basically already a decade collecting fossil leaves in the Dakotas and Montana and collecting literally thousands of leaves and knowing quite well the Cretaceous and Paleocene floras of the Rocky Mountain regions, this site contained many things I'd never seen before. Many things that are only known from this site. And that seemed kind of odd. Big, beautiful, complete, things like this, great preservation, and then just 50% with drip tips. So it seemed that if you were to use those characteristics to recognize a wet, warm place, this place would qualify. And here's just a garden variety leaf from the Amazon and a garden variety leaf from the rainforest in Castle Rock. As we did more work and did the dating of the site, we actually were able to show the site was 64 million years old. So not early Eocene, but in fact early Paleocene. Just 2 million years after the Cretaceous tertiary boundary. And what was kind of cool about the site was it was an in situ site. That is to say, we actually found standing in-place plants. So you can see here where the hammer is, there's a trunk going vertically, and those are roots radiating out on the soil surface. We're able to actually uncover the forest floor itself and see the forest floor, which means that we were able to map then the occurrence of fossils on a landscape next to a highway. And here's, as we dug this, we dig in with backhoes, and then we take the fossils out. And when we were digging here, we realized that we were following these big trails of carbon, and we realized that we'd actually expose the base of quite a large tree. The rope is a ring of carbon. Those other ropes are other linear bands of carbon. What you're looking at here is basically a carbonized base of a gigantic tree trunk. And one of the things that we always think about as when we're casual, sloppy thinkers is, where are the petrified trees? But petrifaction is a process that happens sometimes in areas around volcanoes, but most trees don't get petrified. Most trees rot away. You go for a walk in the forest, the corpses of the dead trees are reduced by termites to carbon dioxide, and the tree goes away. So the fate of most trees is not to become a petrified tree, it's to become carbon dioxide again. So when you walk through forests, you think about the forest, there's not much that tells you about the history of the forest because the trees are basically being returned to the atmosphere. And so it's not a surprise not to find petrified forests, but then you realize you can actually find the traces of trees other ways and start to get a sense of where the trees were. So you start to think, okay, here's what this place must have looked like. Big trees, small trees, and abundant palms. Again, same guy for scale, so you have to adjust your mental thinking. And not only abundant palms, but a bunch of different kinds of palms, right? So there's a host of different palms today. There's a couple thousand species of palms. Palms tend to be plants that don't like places where the ground is frozen. You probably couldn't do too well with palms here in Ithaca, I would imagine. But here in the Denver Basin, we're ample palms, pinnate palms, costa palmate palms, abundant. And then we found this beautiful frond, meter-long frond of a cycad. And while we were digging, we actually realized that we'd found a whole cycad plant. This beautiful thing. There were 25 fronds laid out and a trunk in place. And it was kind of fun because when you work for a museum, you could just call up the evening news. And they came down at 5 o'clock, and we opened this thing, this outcrop, live at 5 on the evening news. Always striving to communicate science whatever possible way. And here's a reconstruction of this still unnamed genus of palms. It's similar to Diowan, but it's not Diowan. And we actually found next to the trunk in place seedlings of the palm in place. So we published, we did an analysis using leaf margin and got a mean annual temperature around 22 degrees C, a mean annual precipitation of over 2 meters of rain, and over 100 different species in the initial analysis. And as we kept digging this site, because there was more road work, and each time they did more road work, they found more fossil sites, so we kept going back. We kept finding more and more species here, and it was a staggeringly diverse fossil site. I mean, fossil leaf sites typically have 5 to 25 species. These sites were producing 60 to 70 species for a single hole in the ground, which would be equivalent to a single grab sample of leaf litter on the forest floor. Think about it that way. And it's actually difficult to get 60 species in a leaf litter sample because when you're even in the most diverse tropical rainforest in Amazonia, you can only pack so many trees into a certain amount of space, and the leaf litter is only capturing the leaf litter from the nearby trees. So it's, even if in Yasuni or Manu, it's pretty rare to get more than 45 or 50 species per leaf sample graph. We're getting as many as 60 here. And here's just a rarefaction curve from one quarry there of just dicot diversity, 73 species from 500 specimens. So hyper-diverse, 64 million year old, tropical rainforest, not in the tropics. And here's just a view of the fossils laid out, the foot-long ruler over there for scale. And this site really kind of rang my bell and said, what in the world's going on here? What does this say about tropical rainforest origins? And I went into the literature and looked for the evidence in the tropics of early tropical rainforest, and it's pretty sparse. It was after this site that the site at Cerrejón in Colombia was discovered, which is late Paleocene, about 6 million years younger than this, as perhaps the best known equatorial tropical rainforest site. So we did a landscape transect here. We had this long hill. We were able to cut into the soil a long length of it, and we did that at many places. You see the lowest layers of the rainforest is, you can see the tree trunks in place. And we then took the common taxa and we censused them along the hill. So you imagine if you're walking through a tropical rainforest, as you walk through the forest, the leaf litter beneath your feet changes its composition as you walk under different trees, because the trees are heterogeneous in distribution in the forest. So as you're walking through the forest, your leaf litter will literally change its composition. And our hypothesis was that we would see the same thing here. And so what you're seeing here is the distribution of this leaf, CR23, large there, lower else. But if we go across the ladder, you can see that these different species appear sometimes broadly distributed, sometimes local, sometimes spiked, all the way across the forest. So there really was like this heterogeneous distribution of species across the landscape at the same exact stratigraphic level, which seems to suggest we have the same heterogeneity that you get in a tropical rainforest. Now, a lot of these things down below are things we'd never seen before, and I started scouring the literature for those species in the paleobotanical literature and coming up pretty dry. We did a painting of this, reconstruction of this landscape, what it looked like, and you can see that the cycad, everything here is based on actual fossils with the exception of the buttresses. The buttresses are an artistic conceit that obviously makes you think tropical rainforest. So I admit that up front. We did not find any buttress trees. That little critter there, that's a Stylonodontine teniodont, which you may not have ever heard before. It's an extinct lineage of mammals that appears in the early Paleocene, goes extinct in the late Eocene, known from probably less than 15 skulls. And while we were doing this excavation, these guys were driving down the road nearby. It's a true story. They stopped to take a leak on the side of the road. While they were taking the leak, they spotted the thing they thought was a coyote skull. They brought it to the museum, And in fact, it was a Paleocene Stylinodontine teniodont. So we actually have one of the denizens of this forest. And it turns out in paleontology that peeing is the best way to find good fossil sites. Because most people don't look at the ground until you're actually like, oh my God, there's a fossil there. So don't ever feel bad about it. It's all good. So now the context of this site is that in the late Cretaceous, there was a seaway that bisected North America. And North America was actually, Western North America was effectively a peninsula of Asia, sitting down. And we were starting to call this peninsula Laramidia. And there was a wide sea that at times was about 1,000 miles wide, 600 feet deep, that separated Laramidia from Appalachia, or effectively flooded most of Kansas and Nebraska. And you can see that Colorado's in that space. If you look at this diagram, you can see in dark red the uplifted rocks of the Rocky Mountain Range. And in the Denver Basin, we can actually date quite precisely the uplift of the Rocky Mountains. As we see in the stratigraphic layers adjacent to the mountains, we see the first appearance of gravels being shed off the mountains. So we know that the Rocky Mountains first breached the surface about 68 million years ago. And this site at Castle Rock is right up against the mountain range. We know the mountain range was there at 64 million years ago. And in fact, we even find lahar deposits, which are lahars are these volcanic mud flows that come off volcanoes. Around Denver there were volcanoes. They're gone because volcanoes are ephemeral, but the debris from volcanoes gets buried. We find lahars that are composed of chunks of volcanic rock and petrified palm trunks. So there's palm-studded volcanoes in Denver sliding off the mountain range into this tropical rainforest landscape. I hope you're getting to see these things when they come in. So here's the location of the Castle Rock Rainforest up at the foot of these mountains. And then sometimes these things are so obvious you don't notice them, but when you go to Denver, you live in Denver, they have a thing called the monsoon, which is not the monsoon of the Himalayas, but they talk about the Denver monsoons. And what the monsoons are is that in the spring and the fall, when there's cold weather coming down from the north and moisture coming off the Gulf of Mexico, you get heavy rainfall on the eastern side of the Rocky Mountains. Those are the monsoons. And so we did some modeling. It turns out in a warmer world, we have a closer, wetter water source. You can predict much higher rainfall on the eastern flanks of these mountains. So this is an orographic effect we're seeing here. That's why we didn't see these things before, is that previous fossil sites weren't close enough to the mountains to actually get enough rainfall to make the rainforest. So it's like, oh yeah, rainforests are truly localized, in fact, to places like volcanoes, which give you localized high elevation and orographic increased rainfall. So that was the sort of the model for this thing. And in Morley's book, he prints this really interesting diagram with not a lot of evidence for it, frankly. He kind of deduced that in the Paleocene there might be as many as 3 bands of tropical rainforest, one equatorial, one mid-latitude north, one mid-latitude south. And that was an interesting hypothesis, and it's curious that the Castle Rock site is pretty much where that northern band is located. So in my mind, that starts to be a compelling story, and then the question is, what's the evidence for that equatorial Paleocene rainforest? We have the one site in Cerrejón in Colombia, but boy, that big band in Central Africa, unexplored. That big band in Amazonia, unexplored. So these are hypotheses, right? We don't really know when the equatorial rainforest kicks in, primarily because lack of exploration and fossils, which is the argument for paleontology in general, is the good stuff is all out there still. So further work on the study, as we started digging into the affinity of these plants, most of our plants seem to have Asian affinities, not South American affinities, which makes sense because they were a peninsula of Asia. In a warm world, you can get stuff across the Bering Land Bridge and down. Obviously, South America is a long ways away. So if there were these 3 bands, you'd have a northern band with Asian affinities, a southern band with Australasian affinities, and who knows about the equatorial stuff. The bit of evidence we have from the pollen record suggests that South America has some input from Africa as well in the Aleutian. Now, just to close this up, my day job now has imperiled my extensive field work, which is annoying in the extreme. But I still continue to do various kinds of public communication of science. I'm doing a 3-hour TV show for Nova about the making of North America. It's a geology of the continent. And they're flying me all over the place. And I'm working with Ray Troll, who's an Alaskan artist, about a book about the West Coast. So those two things, I slip out the door occasionally and disappear into the wilds. And I've been spending a lot of time between Seattle and Fairbanks, up the coast. So one of the questions I have is like, this place today is home of the great temperate rainforest of the Pacific Northwest. So from Northern California all the way up to effectively the latitude of Homer, Alaska, you have temperate, conifer-dominated rainforests. And it occurred to me to ask the question, well, when do those things show up? When do you get your first western red cedars and your Doug firs and your Sitka spruces? When do those kick in gear? When is this forest, this is the forest of my childhood, when does this forest come into being? And so I've now found 3 sites that are pretty interesting in this context. The Chuckanut, the Kootznohu, and the Chickaloon. Great names. None of these are well studied yet. They've all been known for a long time, as most fossil sites have been, but most people who collect fossil sites were collecting the fossils and not thinking about the site or the location. And of course, this is a landscape which is full of exotic terrains. These are chunks of mini-continents that hit the crust of North America and slide upwards to the slot. So there's some northward translation of these things. But it depends where you are on the faults. And we now have looked at these 3 sites which seem to be in a docked position when they were deposited. So they weren't carrying fossils and docking after they had fossils. They were docked and the fossils were buried in those locations. And in Chuckanut in Washington State, which is amazing, is it looks like Castle Rock. There's palms, there's big leaves with drip tips, there's huge leaves, there's cycads. And in Kootznohu, which is, it took me a long time to figure this out. There was a paper in 1911 of a USGS geologist who went to Kupreanof Island, which is east of Sitka in southeast Alaska. And he publishes just a few general sites. He says Hamilton Bay near Kupreanof Island. But in there was an illustration of a cycad and one of the species that I have from Castle Rock in Colorado. So after much negotiation and figuring out where Little Hamilton Bay was and finding the boat to get to Little Hamilton Bay. I went to Hamilton Bay in 2012, and it's a pretty cool place. It's a pretty nondescript bit of coastal Alaska, and we cruised around the bay, and there was almost no outcrop. We're like, well, where was he digging the fossils? And the tide went out. There's about 15 feet of tide there. As the tide went out, you can see slabby stones right at low tide. So we went ashore and started pulling up these big slabs of stone. And there was, on one on the left is actually a Castle Rock species. It's one I've only seen at Castle Rock. And as we dug further, we got into these really curious cycads. With this really, that triangular apex is actually not an accident. We found several with that preserved on them. But just 2 months ago, I took the NOVA crew up there, and at low tide, we popped out a gigantic palm frond at low tide. And as we dug this out, the tide came up and washed over the top of that thing, and we hauled away this thing. We got this still size. It's a 7-foot wide palm frond at latitude 57. So I say to you, Alaskan palm, right? Polar forest Alaskan palm. And where are the Sitka spruce? And it's like, this is a different world again than we've ever thought about. A different forest. Probably in this case, not an orographic forest, but a coastal forest or a coastal orographic kind of situation. A wet, warm landscape. And it turns out, we'll be going back to this spot for sure, but the Chickaloon, which I thought was more of a temperate flora, and this is what you find in museum collections of Chickaloon. Again, the metasequoias, the comptonias, and things like that. It turns out there are palms in Chickaloon as well. So there is this Pacific Northwest coast flora that's only known from a few places, and no one's really kind of put the whole story together yet. But I think it's very curious, what do you want to call this forest? But it's not the forest of today. And it tells me that there's an argument for a lot more field work. And the warm world of the past is a pretty compelling way to talk about climate change, I find, because fossils are data, man. If you show a fossil of a palm in Alaska, and we're redoing the Dinosaur Hall at the Smithsonian now. I arrived there and immediately closed the Dinosaur Hall for its first ever renovation. And it will take us several years to do it. But when we reopen, there'll be this palm frond from Alaska in the exhibit, and it'll just say Alaskan palm. Thank you very much.
So continental drift actually plays a significant role in many ways because North America is moving. In fact, Ellesmere Island is at a lower latitude now than it was when it had those fossils on it. So what you have to do with any fossil site is do your best to reposition it to where it was when the fossils are deposited. Secondly, the continents come together and close off. When South America hits North America, it changes circulation and rainfall locally, or creates mountains. And in addition, these exotic terrains come in and smash into the west side of North America. And basically, the western part of North America is created by microcontinents slamming into the side of North America and sliding north. So there is a flora, for instance, in Washington State called the Winthrop flora. It's about 115 million years old. That looks like the flora that made that was deposited at the latitude of Mexico. And the flora was then buried, fossilized, and that chunk of rock slid up in the position of Washington State. That's the Baja BC concept. They call that, Malcolm McKenna used to call that the Viking funeral ship. You know, the Vikings would, when one of the key Viking guys would pass away, they'd like bury him on the ship and send the ship out to sea. There's a dead guy floating, so it's a dead palm floating. And there's that concept. There's lots of ways that you have to understand your continental lithic tectonics to interpret these things. But once you deconvolve that, the story comes into focus. Yeah.
The idea of a tropical plant community reacting to 3, 4, 5 months of darkness at a time is super weird. Are there any thoughts about, especially if it's migrating, from an area below the Arctic Circle through the Arctic Circle to those extreme variations in daylight hours? Are there any thoughts as to how that's shaping or affecting these plants that are migrating through that area?
So, yeah, this is a really important question, and I think what I showed you, palms is high enough for 61, but 61 is still south of the Arctic Circle. The floors from Ellesmere appear to be all deciduous. So, the deciduousness seems to be a perfectly reasonable response to no light. In fact, you think of deciduousness as a response to cold winters, but it could just as well be a response to no light, right? If there's no light, why have a leaf? So, and if you think about it, there's even an argument that deciduousness started in no light conditions because in a warm world, we're going to get a cold winter. So you might actually have an acceptation from polar darkness from deciduousness that's pre-adapted for life in a cold world which evolves later. So the northern extent of tropics, or for that matter, the southern extent of tropics, remains an interesting question because we're finding tantalizing clues that both across Thuringia and across Scandinavia and across Antarctica, that some things that are pretty tropical manage to get across. So we do have these time periods. There's one called the Paleocene thermal maximum of 56 million years ago, where in an already warm world, in an already ice-free world, there was an abrupt 6-degree centigrade spike. So, and that doesn't last very long, it lasts 100,000 years, but 100,000 years is plenty of time for a monkey to walk from Manchuria to Wyoming. And we think that in those moments, when you have the hyperthermals, we're calling these things, when you have hypothermals, you might be able to squirt tropical adapted taxa across polar land bridges. And that's kind of the interesting thing for me. And we see examples of this both in the north and the south, where things that are pretty thermophilous have representatives on both sides of land bridges. How did they get there? Is a pretty good question. But fully tropical stuff, and once you get away from, you have to be careful about your terminology because tropics definitely means between the Tropic of Capricorn and Cancer. And I've completely abused the use of that terminology in this talk. I'm using tropic to describe a type of plant vegetation or a climate parameter. And so equatorial is probably a better word. But I'm really fascinated by this stuff because I think that it's the reason we haven't been finding these things everywhere is that you need orographic conditions to have the heavy rainfall to give you the evidence, and the temperature is there from other proxies. And it's just a matter of targeting our search image to find more examples of this stuff. Questions about finding forest fires in the fossil record? We certainly find charcoal all the time. So charcoal has got to be a forest fire, and it's actually quite abundant, both macro charcoal and micro charcoal, and of course these charcoalified flowers that these guys working on are evidence of forest fires. And one of the things that's been kind of interesting is that we predict forest fires in the K2 boundary, We don't find the charcoal at the KT boundary. It's very interesting. We find charcoal throughout the Cretaceous and the Paleocene, but actually at the KT boundary itself, we don't see charcoal that's predicted by some of the scenarios of impact. So I'd say there's definitely good evidence for forest fires.
Or if you say it's 70 degrees latitude, what would the winter temperatures, I mean, you're saying the modeling's not very good yet, but I mean, what would winter temperatures get down to?
Well, this is the thing, right? I mean, we've got, I mean, you can do the experiment, take a crocodile and turtle and a snake and see where they go. We don't seem to have palms that far north, and palms don't seem to like frozen ground. So conceivably things that could hibernate or be deciduous, I mean, it may not, they might be fully winters. And then in 2012, I went up to the Colville River in Alaska, and on the Colville River there are bone beds of dinosaurs that are 70 million years old. And I've heard about this for years, I just wanted to check it out. And I found two things when I went there that were kind of surprising me. One was the bone beds are primarily babies. They're small, they're ductile dinosaurs, but most of them are small animals about this big. These are not migrating animals, animals that were born locally and died in some sort of probably a big storm surge off the Beaufort Sea. Because they're literally, I dug 1/3 of a cubic meter of this bone bed and got 260 bones. They're little tiny baby dinosaur bones, and the bone bed went for miles. But also, there are volcanic ash deposits there. And volcanic ash is a really great thing for fossils because if you think about volcanoes, they erupt and the ash rains out of the sky, and it's basically like raining out of rock. And they bury landscapes. So you get Pompeii-like situations. And Pompeii is a great example. Maybe the best fossil site in the world, I would argue, is this site called Ashfall in Nebraska. It's in the middle of nowhere in Nebraska. It's worth going to. It's about 11 million year old ash fall from an eruption that happened in Idaho, and it buried a herd of rhinos in place. And it's amazing that there are baby rhinos next to the mothers. There's birds. I mean, everything is exactly as it happened 11 million years ago. And about 1990, Scott Williams at the Smithsonian found a ashfall buried Cretaceous meadow, where the ash buried an herbaceous Cretaceous landscape with all the plants in growth position. And so you can actually see for the first time what the herbaceous vegetation of the Cretaceous looked like. And when I was up in the Colville River, there were these ash beds, and I just picked one up and looked at the bottom of it, and it was just covered in ferns. So there's this world up there in the Cretaceous that's, I think the other point about the high Arctic warm situation is that because there was a lot of discussion about the Paleocene thermal maximum, it looks like the warmth there was a long time, and the high warmth was sporadic. It was always forested. And so, in my mind, that biome, the Arctic forest biome of the Eocene, is a really cool place to study because of those issues of winter. Darkness, it's got to get cold, right? But people have modeled methane clouds, they've modeled warm currents, they've modeled a variety of ways to keep it from getting frigid. Which I think is the challenge. If I get cold, but it can't get frigid.
No further questions. Let's thank Kirk for a really nice.
This has been a production of Cornell University, on the web at cornell.edu.